Hey everyone, welcome to this live session of your daily equation. It is good to see all of you. It's 3 p.m. here on the East Coast of the United States and a very cloudy day here in upstate New York, where I am at the moment. And I'm looking forward to spending an hour with you guys, hanging out, talking about whatever is on your mind and answering a few questions, arguing with you a little bit if you want to push back on anything that I say that you don't agree with. I'm all too happy to have that kind of an argument. Just put your comments in the chat. Some of you have already asked some questions on Twitter and YouTube. I've got those. So let me just jump right in right now and begin with the first question. I'll pick one at random from the list that I see over here. And okay, Bonnie L asks in the chat, hi, Professor Greene, why does gravity go away in free fall? And that is a deep question. It's a question that people didn't fully realize the answer to that question until Albert Einstein came along in the early part of the 20th century. And I'm going to discuss the general theory of relativity, gravity, the relationship between gravity and acceleration, the relationship between gravity and curvature. I'm going to start that, I don't know, sometime next week is my guess when I'll get into that. But to answer Bonnie's question, here's the idea. So I'll give it in the historical version. So Einstein was sitting in the patent office in Bern, Switzerland. This is about 1907. And he has what he later in life describes as the happiest thought of his entire life. What is the happiest thought in Albert Einstein's entire life? In the patent office, he imagines that there's a painter who is painting a building, and therefore he's high up on a ladder. And Einstein envisions the painter falling off of the ladder. And Einstein imagines what the painter feels as he or she is falling downward. And the key insight that Einstein has is that the painter will not feel their own weight during the descent. And I like to phrase that. I mean, if you imagine that the painter is standing on a scale, and the scale is like Velcroed to the soles of the shoes of the painter. As the painter is falling, imagine the painter is falling feet first. The painter and the scale, they fall at the same rate. That is the deep insight. And that comes right from Isaac Newton's description of gravity, where the force of gravity is proportional to the mass of the object, but the relationship between force and mass, force equals mass times acceleration, means that the mass dependence on the gravitational side and the mass dependence on the acceleration side, they cancel each other out. This is this idea that inertial and gravitational mass are the same. Putting those details to the side, intuitively, because of that, the painter and the scale, they fall at the same rate, which means the painter can't press down on the scale any longer, which means if the painter looks down at the reading of the scale, the painter will find that the reading of the scale drops to zero because the painter is no longer pressing down on the surface of the scale. So that's the sense. If when you're on free fall, the sense of your own weight goes away. And that's basically the idea that, in a sense, gravity is going away. Gravity is this sensation that you have. I mean, right now I feel gravity because my body wants to fall downward under the pull of the Earth's gravity, but my chair is getting in the way. So I feel that force pressing up on the seat. If I was in free fall, however, I wouldn't feel that force. I wouldn't be able to press down on the scale. In that sense, my weight would go to zero. And therefore, in that sense, gravity would go away. My favorite demonstration of this, and I'm thinking I'm going to do this for you all next week, it's so simple. You take a bottle of water. I do have one around here, but I can't actually do the experiment. If I were to take this bottle of water and poke holes in it, we all know the water would spray out of the holes. But the beautiful thing, and I'll show you this next week, is if I then let the bottle go into free fall, the water stops spraying out of the holes. Why? The water sprays out initially because the water feels the force of gravity, and that gravity pulls the water out of the holes of the bottle. But when I let the bottle go in free fall, the water inside no longer feels its own weight like the painter in free fall. If the water doesn't feel its own weight, there's nothing pulling the water out of the holes. The water stops spraying. And indeed, that's exactly what does happen. All right, so that's a nice introduction to things that we're going to talk about next week, general theory of relativity, gravity, and all that kind of good stuff. But let's now move on from there. And what do we know? There's a whole little discussion I see between a variety of people, Ludwig von Beethoven and others, Prayag Das, on free will. Others have chimed into this idea as well. So the question that is being asked is, when we consider the fact that the universe is so random and vast, it's more likely that free will does not exist. Divyesh Raj chimes in. Prayag asks, what exactly is free will? And then I see further down the line that people are noting that, at least from the perspective of how I describe it in my latest book, and as I've described in various other places, the absence of free will emerges from the recognition that every thought you have, every decision you make, every action that you undertake at a microscopic level is nothing but your particles moving one way or another. And the motion of your particles, or more precisely, the quantum mechanical evolution of the state of your particles, is fully governed by mathematical law, mathematical decree. There simply is no opportunity for you to get in on the action and somehow change the mathematical unfolding. So if you're not making those decisions because you are not in charge of the motion of your particles, what is making those decisions? And the answer is the mathematics underlying the fundamental laws of physics, whatever that mathematics might be. So then I see somebody else chiming in and saying, but how then can you explain that people have a sensation of free will? Why does it feel so real? And the answer to that is quite straightforward. There are many sensations we have that are not truly reflecting how nature is constructed. I mean, right now I'm sitting at a table right here. Can you hear it? I'm knocking on the table. The table is made of wood. This table feels like it is completely solid. But you all know that that sensation that I have of sitting at a solid table is misleading, because the true nature of the quantum world establishes that the vast majority of this table is actually empty space. It's just that my knuckles have outer electrons that slam into the outer electrons in the atoms and molecules making up the table, and they repel each other. And that repelling force is what I feel when I try to push my hand through the table. So indeed, I'm unable to push my hand through the table, but it's not because the table is solid. It's because of the way particles interact. And indeed, most of the table is empty space from the standpoint of a kind of classical version of particles making up the ingredients in the world around us. So there you have a nice little example where intuition is a misleading guide to the true nature of the world. And I have to say the same thing about our intuition, that we have free will. It feels real. The sensation is a real sensation that all of us have. And presumably we have it because it has evolutionary value. Presumably our forebears in the African savannah, those that had a sensation that they were in control, that they had freedom of will, they perhaps are the ones that were better able to cope with the challenges in the world around them. And therefore, those who had the tendency to envision that they had free will are the ones that typically would have greater numbers of progeny, thereby seeding future generations with that very same proclivity to imagine that they have a freedom of the will, even though that freedom of the will is not something that truly describes the nature of the world. And that's my view on these ideas. I'm happy for you guys to argue back if you don't agree with that. As I said, I love that back and forth. So I'll wait to see if anybody has anything further to say on it. But let me now jump over to a question that comes to us from YouTube. And it's Petri Vevilanan. Sorry, I feel so bad as I dismember your names. Hello from Helsinki, Finland. Can you explain the idea of loop quantum theory? Please, what is your personal opinion about it? Well, Petri, I can basically. Let me just quickly say, what is loop quantum gravity trying to accomplish? It's trying to accomplish the very same thing that string theory is attempting to accomplish, which is to blend, to meld together our understanding of quantum mechanics, the laws of physics that manifest most strongly in the microscopic realm, with the laws of gravity, the laws of general theory of relativity that manifest most abundantly in the realm of big things like stars and galaxies. And look, this is a puzzle to blend these two theories that we have been seeking to resolve for a very, very long time. And a number of proposals have been put forward. String theory, this idea that the world is fundamentally made of filaments of energy that vibrate in different patterns and so forth. That theory is the one that I and other string theorists have been working on and developing. And on paper, we believe that it does achieve the goal of putting gravity and quantum mechanics together. The challenge is that we don't know if it's the right theory of the world. We haven't been able to experimentally test it or confirm it through observations. And therefore, there's room, ample room, for other approaches to putting gravity and quantum mechanics together. And loop quantum gravity is one such approach. The approach that is taken in loop quantum gravity is to really focus on Einstein's general theory of relativity, to rewrite that theory in a slightly different form than Einstein wrote it down, a form that I think if Einstein were alive today, he would obviously understand it, but he would need the loop quantum gravity community to explain to Einstein what it is that they're doing, why it is that they're writing his beloved theory in this unusual looking form. And in that unusual looking form, it turns out that the means by which we quantize theories, that is, the means by which we go from a classical description of the world to a quantum mechanical description, is easier in these new variables, as they're called, this new approach to writing down Einstein's theory. And so that community believes that they have put gravity and quantum mechanics together by starting with Einstein's theory, rewriting it in this more useful form, and applying the fairly standard rules of quantization that anybody in college, sophomore learns about. From a string theory standpoint, we start in some sense in the more particle physics side of things. We don't start with Einstein's general theory of relativity. We start with the motion of these little tiny filaments, which are meant to be the way in which we think about particles in this new string theoretic description. And what we find, amazingly, is that the equations of string theory naturally yield the equations of the general theory of relativity. We don't start with general relativity. The loop quantum theory people do. And so we like to say that if you were to imagine a history of science on another planet, where for some reason those scientists first came up with string theory before the general theory of relativity, those scientists would have been able to extract the general theory of relativity from their understanding of string theory. So it's as if the loop quantum gravity people start on this end of the story with the general theory of relativity. String theory folks start on this other end, more from a particle physics, more, if you will, quantum mechanical description of the world. And we each go forward trying to blend the other theory into the story. Now, do these two approaches miss each other? Do they go in completely oblique directions? Do they meet in the middle? These are questions that at the moment we can't address. But I'm glad that there are different approaches that people are taking to put gravity and quantum mechanics together. All right, so what do we have over here on the live chat from YouTube? Hey, Mr. Brian, can a particle really go back in space, or is that a misconception? Really go back in space? I'm not sure what that means. Sure, I mean, particles can go any direction in space. Maybe the question is, can a particle go back in time? And for that, I know that there are many descriptions out there in the wider world in which quantum mechanics is described in terms of sort of particles going forward in time, antiparticles going backward in time. It's a useful way of thinking about quantum mechanics for some applications, but I consider it kind of deeply misleading at a more 30,000-foot level, even in standard quantum mechanics, things are really evolving in one temporal direction. It's not as though there's time travel embedded in the quantum mechanical laws of nature. Rather, when we want to talk about traveling to the past, we have to introduce much more exotic ingredients, many more things that we don't even know if they're realized in the world. Things like wormholes, things like the ability to pass through a wormhole, things like the ability to grab hold of the openings of a wormhole, move them relative to each other, take one opening, put it near the edge of a black hole. I mean, it's fairly exotic stuff when we try to talk about things going backward in time. And most of us are far from convinced that this kind of backward time travel is possible. Indeed, most of us feel that when we understand physics better, traveling to the past will likely be ruled out, but the door, in some sense, is still open. All right, so I seem to always do this. I have a real nice question I'm about to address. I touch the scroll here, and then it rapidly scrolls by, and I miss it. So sorry. There's one on entanglement. If anyone wants to ask that question again about entanglement and faster than the speed of light, I'd be happy to address it. Just answer it one more time. Not answer it, ask it one more time. What else do we have here? Let's see. What will so Rufat, the mathematician, asks, what will the next major discovery be in physics? And well, it depends on what you're asking, at what level you're asking that question. There's a lot of exciting work happening in gravitational wave physics right now. And we have long since realized that every time we develop a new means of examining the wider cosmos, we learn new stuff. And so in the last couple of years, we've developed, finally, it's been 50 years in the making, this ability to examine the cosmos, not with light waves, but with gravitational waves. And with gravitational waves, you access the wider reality in a new way. And already people are learning things about nucleosynthesis, where complex atoms come from. Collisions between neutron stars is a approach that really has gained currency through the observations made with gravitational wave observatories. But that's just the tip of the iceberg. We're going to be having all sorts of breakthroughs coming from gravitational wave physics in the next few years, next decade. So that's certainly an incredibly exciting arena. But if you're asking the question at a more global level, what next breakthrough do I feel we really need in order to make that leap to the next big understanding of the universe? My guess is that it's a deeper understanding regarding what space and time actually are. You may be familiar from my books or from other YouTube videos, your own studies, that ever since Einstein, we have learned so much about the phenomenon that can occur within space and time and the qualities that space and time have that are not intuitive. The fact that time slows down for an object in motion, the fact that length contracts along the direction of motion, the fact that time is warped near a gravitational body, and that warpage can become quite significant near a strong source of gravity like a black hole. I mean, all of these things are wild. They're wonderful insights, but none of them give us any understanding of what space is, what time is, right? We think about space as the arena within which events take place. We consider time the variable that allows events to occur not simultaneously, that they can spread out along this other axis, the temporal coordinate. But fundamentally, could it be that space is made of ingredients like molecules of space, just like material objects are made of collections of molecules? Could time itself be made of atoms or molecules of time? And what would those atoms and molecules of time be like? What are they about? I think these are the kinds of questions that will need to be answered to really ignite the next revolution in our understanding of fundamental physics. All right, what do we have here? Nihilistic Bro asks, Professor, doesn't quantum mechanics allow free will? Can't then our consciousness and free will be a product of the quantum nature of physical laws? And it's a natural way of retorting against my argument that we don't have the free will that we think that we do. So, nihilistic bro, I know exactly where you're coming from. But the answer that I have is that I do not think that quantum mechanics helps at all. Quantum mechanics certainly changes our understanding of how the universe unfolds. In a classical description, the universe unfolds in a deterministic manner, in the sense that if you tell me how things are today, the laws tell you precisely how they will be tomorrow. And that would seem to rule out free will immediately, right? If you tell me how things were before I was born, and that data is enough to determine what's going to happen tomorrow, then what freedom do I have if that future is fully determined by the past together with the fundamental laws of cosmological unfolding? Quantum mechanics comes along, and this is where nihilistic bros intuition, I believe, is coming from. Quantum mechanics comes along and injects an element of happenstance, an element of probability in the unfolding, so that if you tell me how things are today, the best I can do is predict the probability of how they will be tomorrow. 30% chance this way, 20% chance that way, 50% chance another way still. And so within that probabilistic description, the natural thought is maybe free will chooses which outcome actually happens tomorrow. Maybe the laws of physics just give us a menu of possibilities, and then it's up to human freedom to choose which outcome actually happens. And based on our current understanding of quantum mechanics, that is simply a wrong description of how the universe unfolds. The outcome is a random choice that occurs in a manner that we've yet to fully nail down, but the data that we have from observation and experiment shows us that the outcome of a given quantum mechanical experiment is random. It's not chosen. We can't volitionally choose the outcome, because if we did, the data would not show the random quality that it does. And randomness is not what we mean by freedom. If I told you that your choices were determined not by a classical Newtonian progression, but by somebody behind your back flipping a coin, and based on the random outcome of that coin flip, you make one decision or another. If that is what's going on, I think that you would agree that violates your intuition of the freedom that you think you have. Randomness is not freedom, and therefore quantum mechanics does not help us at all. In fact, I like to say it the following way. If you believe, and I certainly do, but if you believe that the universe unfolds in a lawful manner, I don't care what the laws are, but if you agree that all you need to know to determine how the universe unfolds is that there's a lawful progression from today to tomorrow, determined by laws of physics that we may not even have in our possession, then there's no opportunity for free will. There's no place for you to get in on the action, because the laws determine, in the sense, even a probabilistic sense, the laws are what reality relies upon for the future unfolding based upon the conditions in the past. And that's all there is to it. And therefore, there's no opportunity for free will to get in on the progression. So that's what I have to say on that subject. Again, if you want to argue back, please do. But let's see what else we have here. Oh, please stop scrolling. How do I get, okay, stop. Amanda asks, wait, Amanda, you just retracted your message. Why? It was a very good question, Amanda, and I remember what it says. So I'm going to ask Amanda's question, even though Amanda seems no longer to want me to ask that question. But Amanda said, doesn't that disturb you? Doesn't it disturb me that I don't have the free will that I think that I have? And it doesn't. It doesn't, because where I feel good about my place in the world does not come from this misguided notion, in my view. And again, I say in my view, I'm not trying to be dogmatic about things. You prove me wrong and I'll change my perspective, but nobody has. But I don't gain my sense of value and worth from being able to triumph over the laws of physics. I gain my sense of value and worth from recognizing that, unlike this glass of murky water that people chime in whenever I drink, Earl Grey and soy milk. Unlike this glass of tea, this cup of tea, I can do things that are within my behavioral repertoire that are not in the behavioral repertoire for the cup of tea. The cup of tea just hangs out there. And no matter what I do to it, at most it moves or it shimmies, it shakes, it spills, it breaks. But that's the only kind of behavior that the cup of tea can undertake. Because I'm so more fully developed, refined, and organized in my particulate arrangement compared to that of the cup of tea, can do so many more things. I can think, feel, reflect. I can puzzle about things. I can work on the equations of quantum mechanics. I can talk to you right now. I can respond to the stimulus of your questions written down in a chat bar that I'm seeing on a screen. The cup of tea can't do that. I am not freely choosing my responses. I'm not freely choosing the motion of my hands. I'm not freely choosing my actions. But I am thrilled by the fact that my range of behavioral responses is so spectacularly broad compared to the inanimate world. So my freedom is not freedom to triumph over the mathematical laws of the universe. My freedom is to be released from the bondage of limited behavioral response that constrains the inanimate world. I have been released from that, and so have you. Evolution has released us from that bondage, and that's where we should get a sense of value from. That's what we should feel good about, not triumphing over mathematical laws. Okay, so back to maybe some more concrete physics stuff. Brandon Wood says, can you discuss Eric Weinstein's geometric unity theory? And I can't. And I guess enough people ask me about this theory that maybe I should spend a little while immersing myself in it to get a fuller sense of what it is. I can only speak secondhand. And what I've heard secondhand from people that I trust is that there's not a whole lot to this theory. That could be wrong. Maybe Eric Weinstein is the next Einstein or the Ramanujan, off in left field. I know he was a math major, I think, at Harvard. I read something, and I know that his experience was less than happy one at Harvard, and felt that there was this sort of old boys network behind the scenes that was really determining what papers get published and what works are paid attention to. And I don't know, whenever I hear that kind of conspiracy theory behind the deep state of mathematics and physics, what can I say? I don't see any evidence for it. I've been in the field, in the thick of the field now since, call it from when I graduated with my PhD, 1987 or something. So whatever, 33 years. I publish papers, I referee papers, I speak at conferences, I organize conferences, and the only thing that matters to me and to the folks that I have spent decades working with is the quality of the ideas. We are open to having our ideas smashed to pieces and having the new upstart come in and revolutionize our understanding of things. We love that. We don't suppress that. We don't try to somehow keep the status quo. We love changing our perspective based on observation, experiment, deep mathematical insight. So I don't know, I just get this sinking feeling whenever there's somebody who's making a statement about the controlling forces in the world of math and physics that are somehow suppressing the new ideas from rising to the top. Nothing, in my experience, could be further from the truth. But who knows? Maybe I've had blinders on. I don't think so. Maybe I've had blinders on for the last 35 years, and there's all this dark stuff happening just behind the closed doors of each physics department. But it seems ludicrous to me. And again, I don't want to put words into anybody's mouth. If that's not what Eric Weinstein or anybody else is saying, I could completely be wrong. But just let me speak from my own perspective. There's nothing like that as far as I understand. Okay. Fella Super says, how do you as a physicist come up with new ideas? Well, the new ideas are few and far between, I have to say. And when I say new ideas, I mean really big new ideas. I mean, all of us come up with new ideas and trying to solve whatever limited research problem that we're faced with at a given moment. And those little moments of creativity, those little moments of progress are what keep us going. That's really exciting. But the real big ideas, where do they come from? Whew, I don't know. I mean, I have only had a handful, a small handful, maybe hand, it's too many, maybe three or four over the course of a lifetime that seem to really make a difference in what people work on and the kinds of things that really advance understanding. And usually it's a matter of a lot of hard work. You're beating your head against the wall trying to solve a problem, and all of a sudden there is just a new pattern that you see finally. I mean, I think that's what we are. We as a species are these pattern recognition machines. And most of our pattern recognition has been developed over the course of evolutionary history so that we can get the next meal, we can find mates, we can build shelters, we can survive in a hostile environment. And some of us are the product of that long lineage, but are so enamored by pattern in the external world that we develop mathematical ideas to embrace the subtle patterns, the patterns that you don't need to survive, the patterns that have to do with the motion of the planets, patterns that have to do with the motion of electrons and quarks. And we write down the laws of classical mechanics, the laws of quantum physics. And then we go further and we try to find mathematical articulations of patterns about things that we can't even yet see, the blending of quantum mechanics and the general theory of relativity. So we try to find patterns in the patterns of the mathematics used to describe the patterns that are out there in the world. And it's really a matter of refining your sense of pattern to be able to recognize when there's a new configuration that puts together things that we once thought to be separate. And that blending of things that we once thought to be separate is really the core of the creative process as a scientist. All right. So Yixi asks, do you think if Einstein had known what we know now, he'd be able to finish his theory of everything? I don't think so. There was a time when the deep questions were accessible to a single brilliant mind. And in the early part of 20th century, that mind was Albert Einstein. I mean, there are many people around Einstein who did a lot of the groundwork that helped his own thinking. But, in the general theory of relativity, it was largely the genius of Einstein that was pushing these radical ideas forward, even against the advice of others like Max Planck, who told Einstein, stop it, don't work on gravity. You're not going to get to the answer. And if you do, he even said, no one will believe the answer that you come up with. These ideas are just too complicated. They're beyond the reach of our current understanding of physics, is what Planck was saying. But Einstein didn't listen to that, came up with the general theory of relativity. And again, just to go to the point that I mentioned before, when he put forward the general theory of relativity, people read the paper, people understood the paper, people changed their way of thinking about things because of this new insight. No one tried to suppress Einstein because the brilliance of his ideas blazed through the dark corners of reality, and nobody could mistake them for anything but deep progress in our understanding of the world. Now, we would love that to happen with our current understanding, but I don't think it's a single person job anymore. I think the issues at hand are so significant and they're so distant from observation and experiment, and they require such a broad range of mathematical expertise that I think it's a communal effort. I mean, who knows? Maybe some new genius will come along and that person single-handedly will come up with a unified theory and that will be it. That's possible, I guess. I just think it's unlikely. All right, so let's see, what do we have? Maybe I'll go back to some YouTube question. What do we have here? Wow, some of these questions I've already dealt with. I don't know. I'm not finding anything there that really fires me up. So I'm gonna go back to the YouTube feed over here. Kevin asks, will the strings of string theory be made of individual constituents that are, smaller still? And Kevin, I don't know. Certainly, if I was to answer based on historical precedent, it is the case that every time we introduce some new fundamental ingredient, new entity, there's something further inside, right? I mean, you get down to molecules. Molecules are made of atoms, as you know. Atoms, you got the central nucleus, protons and neutrons. You got the electron cloud, and then even you go inside protons and neutrons, and you learn back in the 1960s that they have quarks inside of them. Now, if the idea of string theory is true, big if, but for the purposes of this question, imagine string theory is true. You go inside quarks or electrons and you find something else, this vibrating filament. Is that the end of the story? Or could it be that even if that is true, as Kevin asks, there's a finer entity inside of strings themselves? And people have certainly studied the possibility that there are finer entities that make up the strings of string theory. And those are very interesting studies. But even those studies posit an ingredient like D0 particles and various objects that come out of the mathematical description of string theory. So you could just translate your question to those ingredients, whatever they might be, and say, are they the end of the line? So the overall question that you're asking, Kevin, is will we ever get to a point when we've identified ingredients that we can say that's it? Nothing finer to be found. That journey is over. And I do believe that we could get to that point. I do not think by any means that it's necessarily the case that as we go deeper and deeper and deeper, we will always find more and more new stuff. The chapter that has been searching for the deepest reductionist understanding of physical law is a story that may come to an end. Have we reached the end yet with string theory? I don't even know if string theory is right. And even if it is right, there's nothing to say that we've necessarily reached the reductionist end. But speaking more generally, I do think that reductionism is not an infinite progression necessarily. It is something that could indeed come to an end. All right, other questions to ask. Well, actually, here's a question that's not in the Twitter feed, but a friend of mine asked it to me just the other day. A friend of mine named Ken Weinberg, brilliant architect. Maybe he's even listening right now. I have no idea. But yeah, he designed even the space that I'm in right now, my apartment in New York. So in some strange sense, I live in the vision of this individual, Ken Weinberg, since he designed all these spaces that I spend like 80% of my life. And he asked me the following question. He says, look, in these live sessions, he says, you always say the truth. You never say anything that's incorrect. But he said, sometimes he feels that I allow you folks who are talking to me to have the impression that certain weird qualities of the world might be true, when in reality, I fully anticipate that they're not true. For instance, there are sometimes people that ask about quantum entanglement. Maybe minds can be entangled. No. There's some people, I think last time, that asked about the multiverse and whether versions of us might exist in those other universes, and that might give us some means of immortality that we would carry on in the other universes. And my view of these far outstanding ideas is this. The most important thing that I can do in these kinds of conversations is give you insight into what modern physics says about the objective workings of the world, the stuff that's out there that is amenable to third-party objective measurement, observation. We can all go out there and measure it and check it, at least in principle. And that's what physics is about. What physics is not particularly good at is the reverse journey, not into the outer world, but into the inner world of conscious experience. We've spoken about free will, the inner world of spiritual exploration, trying to understand your place in the grand cosmic order, trying to understand the kind of responses that we human beings have to the things in the world, the kind of anxieties that we might have, the kinds of goals, achievements that we might seek out in the wider world. And that's not the place where physics gives us particular insight. So I'm quite open when people are thinking about that journey in language or in ideas that are distinct from the ideas that I know to be true in describing the external world. Will I let you get away with wild sounding ideas like quantum entanglement means our brains may be entangled, or that ESP might originate in quantum entanglement? Absolutely not. That's utter nonsense. But am I sympathetic to the notion that in trying to deal with our own mortality, we may tell ourselves stories that are incompatible with the external world, and we may even know that, and yet we're willing to allow those stories to inform the way we feel about our lives in the wider world? I am sympathetic to that. I mean, I've said on occasion, and I'll say it here too, I don't really care, on occasion, I do things like imagine I'm talking to my father who's been dead for over 30 years. I imagine sometimes that he's actually even watching or enjoying some of the things that are happening, some of the things that I'm doing, and so forth. Do I literally believe that? Is that compatible with my understanding of how the physical universe works? Absolutely not. That's nuttiness, craziness, if you are imagining that it's actually an objective quality of the external world. But as an internal coping mechanism, as something that allows me to have a richer inner life that I find pleasing. Does it make sense from that perspective? It does. So as long as you or I or anybody is able to distinguish between the true objective qualities of the world, the things that are really out there, and I don't care what it is, from quantum mechanics to climate change, okay? These are unassailable things that are happening in the external world. If you can distinguish that between the things that you may use to have your own existence be more comfortable or make sense to you or be richer, if you can distinguish between the two, then allow your inner world to do whatever your creative imagination leads you to. And that to me is a perfectly fine way of existing in the world. Okay, back to some perhaps more physicsy stuff. Azan Naeem asks, Sir, what is the speed of gravity? What is the speed of gravity? Answer to that question is the speed of gravity is equal to 671 million miles per hour, 300 million meters per second. It is equal to the speed of light. So, one of the deep insights in Einstein's general theory of relativity is that gravity does not travel instantaneously from one point to another. In Isaac Newton's description of gravity, gravity is an instantaneous force, right? When you look at Newton's equation, F equals G m1 m2 over r squared, there's no time in that equation, which means that if you were to change the value of one of two masses, maybe this is the Earth and this is the sun, if you were to change the mass of the sun, then immediately in that equation, the value of the force would differ. If you cut the mass of the sun in half, then according to that equation, F equals G m1 m2 over r squared, the force that the Earth would experience would be cut down by a factor of 2 immediately. There's no time delay in Newton's equation. And Einstein comes along and says, that's not right. That can't work. That would allow influences that can carry information to travel at a speed that's bigger than the speed of light. He realized that wasn't possible. So in the general theory of relativity, he fixes this problem with Newton's theory. And in this description, gravity is transmitted by warps and curves rippling through the fabric of space-time, and those ripples travel at the speed of light. And therefore, the speed of light and the speed of gravity are one and the same thing. This fixes the problem with Newton's version of gravity and gives us our deepest understanding of the force of gravity. And that actually reminds me of another question I saw in the scroll. I wish I could credit the person who asked it, but there was a question, I don't know, about 20 minutes ago about entanglement and entanglement violating the limit on the speed of light, right? Because I mean, if you imagine, as we discussed it, you got these particles that are spinning up and spinning down, and the idea was each is a 50-50 mixture. You measure one, and it makes the distant particle snap out of the quantum haze, much as the initial particle snaps out of the haze. And that would seem to be an instantaneous influence. You do a measurement over here, and it instantaneously affects the particle over here. That would seem to violate the limit set by the speed of light. And I totally get that intuition. But when you look more closely, the speed limit set by the speed of light survives barely because, in a sense, what Einstein's limit on the speed of anything through space was delineating is a limit on how fast any kind of influence that carries information can travel from one point in the universe to another, right? Right now, I am communicating information to you, right? I'm not even talking about the content of what I'm saying. I, however, right now, am causing your eardrums to vibrate. And it's, of course, not an instantaneous signal. It's vibrating from my vocal cords through my mouth into the microphones in this room, through the internet, and into your ears, right? But the idea is that if I try to communicate to you using quantum entanglement, not that standard approach of sending a sound wave, I would fail. Why? I mean, think about it. Here you got these two distant particles. They're each in a 50-50 mixture in up and down. If I'm over here and want to send a message over there, what I want to do is say, hey, if the particle, say, winds up spinning down, then sell Amazon stock. Let's say that's the information I want to send to you. But here's the thing. I can't control whether this one is going to be up or down upon measurement. And therefore, if this one turned out down, this one would be up. So I wouldn't be sending you the information that I want. The point is, the outcome is random. It's just at both of these locations, the random results are correlated. But I can't control the outcome at one place or another. And therefore, I can't control the information. Therefore, I can't send information. Therefore, this influence, however spooky and odd it may seem, does not carry information from place to place. And in that sense, does not violate this way of framing Einstein's dictum that nothing in the sense of no information can travel faster than the speed of light. But yes, it is a close call, and not everybody agrees with the description I've given here. So that's the other side of the story too. And if you want more detail on that, you can look at my book, Fabric of the Cosmos. One of the chapters on entanglement, maybe is chapter 6 or something, I can't remember now. I go through the various ways in which people have responded to the possibility that entanglement might violate the speed of light limit. Okay. Let's see what else we have here. Darn, here we go. Global Digital Direct Subsidiary Democracy asks, if mathematics is so almighty and lawful, why does it have the holes that Gödel exposed? So yeah, it's an interesting question. It's not that Gödel exposed holes in mathematics. What Gödel did was to establish the limits of the kinds of things that mathematics is able to prove. And Gödel established that there can be true statements within a given mathematical formalism that lie beyond the reach of that formal system, that could not be proved true within the axioms of that system itself. This is a shocking result. It's a surprising result, but it's not a hole in mathematics. It is an advance in our understanding of the kinds of issues that mathematical analysis is able to encapsulate. Now, perhaps what you're asking, person from Global Digital Direct Subsidiary Democracy, is what if the physical universe has a Gödelian-like quality and there are aspects of the unfolding of reality that are beyond the reach of mathematical description? And that is a subtle question. I don't think that is the case. You might say, well, hey, if it's true for mathematics and mathematics are the underlying laws of physics, so aren't you stuck? No, because Gödel proved his theorem within a certain set of assumptions. And those assumptions may not hold true for the mathematical system that truly describes the fundamental laws of physics. So, I mean, there's one fun little example of that. Gödel's using the standard logic that I think we all have an intuition about, but there are other versions of logic. I'm not saying this is how the world works, but just as an existence proof, there are kinds of logic that are called paraconsistent logics, in which a statement and its negation can actually both be true, but you can't concatenate them in a manner that will allow you to prove that anything is true. And so there are these kinds of logics, and in those logical systems, Gödel's ideas don't actually follow. So if it were the case, for instance, just again as an existence argument, that one of the other kinds of logics was actually relevant to the true mathematics underlying physical law, then Gödel's insight wouldn't even apply. So I'm not saying that that's the answer, but I'm saying it's far too quick to say that once Gödel proved the incompleteness theorem in mathematics, then physics is necessarily incomplete. Doesn't follow, doesn't necessarily work that way. Okay. Luil Likes Fire asks, is there an explanation for wave-particle duality? And that's basically saying, is there an explanation for quantum mechanics, why the world is quantum mechanical? And I don't really have an explanation. I don't think anybody does. It could have been the case that our world was governed by classical laws, the ones that Isaac Newton gave us, and that could have been it. It could have been that F equals ma with various choices for F was it. And this law written down in the late 1600s would have been the end of the story. And it just so happens that it's not it. It just so happens that as we dug deeper, we realized that there were limitations to the applicability of Newton's ideas, and that forced us to develop these quantum ideas in which, as Luil Likes Fire asks, there is this wave nature of matter and this particle nature of matter. But logically speaking, could I imagine a universe in which there wasn't wave-particle duality? I can imagine it. Is it somehow deeply inconsistent? Maybe, and maybe therefore the answer to your question is consistency alone somehow demands that quantum mechanics is part of the story, and therefore wave-particle duality is part of the story. I don't know. But what I do know is if you allow for wave-particle duality, and if you write down the equations that describe it, and if you use those equations to try to say things about the external world, the predictions emerging from those equations are spot on accurate. And so the way we physicists tend to look at it is nature demands that we use a quantum mechanical description in order to have an accurate explanation of what's happening in the external world. But it's hard for us to say that it had to be that way. It's hard for us to say that there is some deeper explanation for why the world is quantum mechanical. All right, what else do we have here? Rajav asks, hi, what are your thoughts on the true nature of space on the basis of quantum entanglement, sort of in the holographic projection ideas that have emerged from people like Gerard 't Hooft and Lenny Susskind? And look, Rajav, I think that is the deep question. I don't know the answer to it. In the Newtonian description, you had space. It just was the arena, static arena in which events take place. You had time, which was this cosmic clock ticking forward second after second, the same for everybody. Einstein comes along a few hundred years later, changes that. He says, no, space is not just a stage. Space warps and curves in response to the stuff within the universe, and therefore space is part of the cosmological unfolding, and time is as well, and writes down new equations. Quantum mechanics comes along and describes this quality of entanglement where distant particles act as though they are right next to each other. And then string theoretic ideas come along and take that progression even further, envisioning that the world around us is nothing but a holographic projection of laws and processes taking place on some distant two-dimensional surface that surrounds us, much as a two-dimensional piece of plastic, when illuminated correctly, yields a realistic three-dimensional image. We would be the three-dimensional image emerging from the laws of physics projecting through this holographic surface that surrounds us. And yes, are these ideas revolutionizing or seeding a revolution in our understanding of space and time? Absolutely. And that understanding is currently underway. There are a lot of folks who are trying to understand how the fabric of space perhaps is actually stitched together by the threads of quantum entanglement. Wonderfully exciting idea. We've done programs on this at the World Science Festival. You should check out a program that I moderated with Mark von Ramsdorf and other leaders in the field. I can't remember the name of the program off the top of my head, but maybe we'll link it and you can take a look at that. But it's an unfinished story. And so I don't know the answer to how to really think about space and time in light of these recent developments. But as I mentioned, I don't know, about 20 minutes ago, in answer to another question, I think the big revolution will happen, Rajav, when we finally do have the full answer to the insightful question that you ask. Ernest asks, do you think the Higgs boson contributes to the mass of space-time? I don't think it does. I know it does. So when we talk about the mass energy that is permeating space, we need to include every source. And one such source is this field permeating space called the Higgs field. That Higgs field, that sort of cosmic molasses, not the best metaphor, but not a bad one for having in mind what the Higgs does. This Higgs field has energy, and that energy translates into, if you will, an equivalent amount of mass. And when we map out the totality of the mass energy that is filling the universe, the Higgs is one such contribution. So it's not a dominant contribution. The dark energy, which perhaps is a Higgs-like field, is a much more significant component of the mass energy of the universe. Something like 68% of the mass energy of the universe is contained in this uniform field filling space called the dark energy. But the Higgs is an analogous contribution, is just much smaller. Okay, what do we have here? Well, Greg Gutfield asks a question, but I don't know. I'm not so into describing that question, so I'm going to skip your question, Greg. Clean it up next time, buddy, if you will. What else do we have here? Let's see. Mohammed asked, do you believe in the simulation hypothesis? This is a good question that kind of comes back to the issue that my friend Ken Weinberg raised. Do I allow for the simulation hypothesis? It's a wild, crazy sounding idea, right? That we right now might be within some futuristic supercomputer simulating beings like ourselves, and we think that we are consciously out in the real world when in actuality we are just motions of electrons coursing through a futuristic circuit in some powerful supercomputer. Do I allow for that possibility? I do allow for that possibility. Do I think it's likely to be the case? I don't even know how to describe likely here, but if I just go with my gut sensation, I'd say no. I think this world is real. I think that's the case. Now, I have to admit, if it's a good enough simulation, the simulator would have been able to make me think that it's real. And indeed, I think, as I mentioned in one of these sessions, Oxford philosopher Nick Bostrom makes an argument that if we can ever create simulated worlds and supercomputers, they may be a dime a dozen. It may be very inexpensive to buy one of those computers in the future, and everybody is firing up their own universe simulation, creating a huge range of simulated conscious beings. And therefore, the number of simulated conscious beings compared to the number of real conscious beings would be enormous. There'd be many more beings in a computer than there would be walking around in the real world. And therefore, if you ask yourself, are you real or simulated? The odds would seem to suggest that you are simulated. So, it is a crazy, wild sounding idea, and it is kind of crazy. It's worth taking seriously because it allows us to reframe certain kinds of questions in a way that you may or may not find useful. But if you ask me, do I walk around the world truly imagining that there is some simulator outside of this universe that has set up this computer system that we are inhabiting? No, I don't really think that way. But I do find it useful, for instance, when people talk about the existence of a God, almost always they think about that in the context of a supernatural being, a being that stands outside the bounds of physical law. But the nice thing about this simulated version of having a creator is that creator could well be subject to the physical laws in the real world. And therefore, that kid, maybe it's a kid in a garage, in a futuristic garage that just got a supercomputer for Christmas and has fired up that supercomputer. And here we are talking about the possibility that we are simulated beings, and we are doing this in that kid's simulation. That kid would be our creator by definition, but there'd be nothing supernatural. I don't think that's really the reality, but I like the idea for giving me and others a way of thinking about a world that has a creator that need not be simulated, that can be subject to physical law. All right, so we're coming up on an hour here. I don't know, maybe I'll do one more here if I can find one that's kind of cool to do. Oh, come on, I had one and then it scrolled by again. I guess I can't have my thing on this. Yes. So Mario asks from Chile an interesting question. Professor Greene, what would the result of simultaneously measuring the properties of two entangled particles separated by a meaningful distance in the same frame of reference be? And the answer to that, and I understand why you're asking that question. You're saying, look, if I always talk about you measure this one, it affects this one, or you measure this one, it affects that one. And it makes it sound as though you couldn't sort of measure them both together. There might be sort of a clash where this one wants to affect this one and this one wants to affect that one. And what would happen? Would it fall apart? Would the physical process somehow be inconsistent? And the answer is, look, it's simply the case that these two particles are perfectly correlated if the quantum state is set up correctly. So, if you were to measure this one and this one simultaneously, this one up, that one down, you would get the consistent results that they are anti-correlated, or the result would happen. So, in that particular case, the language of sort of which affected which would be difficult to apply in that particular case. But nevertheless, the result would be perfectly consistent with the quantum mechanical prediction, which is when this is up, that's down. When this is up, that's down, and vice versa. So there really wouldn't be anything particularly striking there. Moreover, and I don't mean to complicate things unnecessarily, if somebody was in a different frame of reference, and I believe that Mario understands this based on the framing of the question, if somebody was in a different frame of reference, watching these two simultaneous measurements taking place in, say, this frame of reference, from their perspective, their notion of simultaneity would be different from the simultaneity in this frame. And therefore, they would say that one person measured first and the other second. And so their description would indeed involve, say, this particle being measured affecting that one, this particle being measured depending on how they are moving. And so from that perspective, even if those measurements are simultaneous in one frame, they're not simultaneous in another. And so the description that I gave would be applicable in that other frame. All right, so what should I do? One more before we get out of here? Victor, I'll give you the final question, Victor. Victor asks, what do you think about quantum Darwinism? And it depends exactly what you mean by quantum Darwinism. It's certainly the case that quantum mechanics applies to everything. It applies to the particles that make up life. It applies to the particles in a block of American cheese. It applies to the particles making up this murky Earl Grey tea that I will no longer touch because it's like spoiled by now. So quantum mechanics is at work in everything. And therefore, it's certainly involved in the underlying physical processes behind Darwinian evolution. But it goes beyond that. I'm not sure this is what you're asking, Victor, but I'll finish with this following thought. Most of us, when we learned about Darwinian evolution and natural selection, we learned about it in the context of how species yield ever wider range of species in the future. On the origin of species is the context in which Darwin described this idea. And what we've learned in decades, centuries since, is that the Darwinian notion of natural selection is much more general. You don't need living systems. Even if you have molecules, okay, molecules that learn the trick of making copies of themselves. And it's a beautiful trick. It's a trick that molecules can learn. They can learn to drag in to their environment the very kinds of particles out of which they are constituted, And the initial molecule can serve as a template for building a copy of itself. It's like DNA, but DNA needs the structure of life. So imagine a kind of DNA-like molecule, but without all of the architecture of life already in existence. And once molecules learn how to replicate, then you have a notion of natural selection, because those molecules that can replicate faster, in a more stable manner, in a more efficient manner, are going to win out. They're going to grab in more and more of the natural resources, the particles, the environment, create more and more copies of themselves. So they will dominate the molecular demographics. It's a kind of chemical combat, is how I describe it in the new book that I came out with a couple months ago, Until the End of Time. You can read more about it there. But the point is that you have natural selection at the level of molecules, because when a mutation happens, if that mutation allows that molecule to do an even better job at making copies of itself, it will beat out its parent, and it will then dominate the molecular demographics. So all of these processes ultimately rely on quantum mechanics and quantum physics. There is a notion of Darwinian natural selection at the level of particles, where quantum mechanics really shows its true colors. But nothing about this is fundamentally quantum mechanical. It's just the way the universe evolves. And therefore, I wouldn't want to inject too much of quantum thinking as at the essence of Darwinian natural selection acting itself out on molecules. But nevertheless, yes, I do agree that quantum mechanics is part of that story at the most basic level of the ingredients and the laws that govern how those ingredients behave. All right, so we're at 4:07. I'm pretty tuckered out. I hope you enjoyed this live session. And I anticipate picking up your daily equation with a new episode on Monday. Let me just quickly note, as you may have noticed if you're following the series, on occasion, there's too much going on for me to get a new episode out on a given day. I'll apologize now at the outset when that happens, but I'll always try to give like a little message and suggest other videos that I have been involved with that you might enjoy watching. And hopefully that's a reasonable substitute in those days, but it will keep going. Again, I don't know how long we're going to keep your daily equation going. I've been having fun doing it. I feel like some of the episodes have been getting more and more technical, so maybe that needs to be scaled back and try to find, maybe you should let me know actually. Do you want things to be less technical in your daily equation, more of the ideas and less of the math? Or do you like more of the math at the level, say, that I've been doing in the last few episodes? I'd really be interested to hear your views on that. But next week, I think I'm going to do a little bit more quantum mechanics, maybe Bell's theorem, if I can work up the courage to try to do that. Maybe the Feynman path integral, the basic idea there. And then I'll turn to, I think, general relativity, the basic idea of metrics and curvature, apply that to cosmology, understand the Big Bang at the level of Einstein's equations, and then who knows? Maybe we'll be done, or maybe we'll carry on from there. I'm going to leave that open. Okay, anyway, it's been a fun hour and 9 minutes to spend with you this Friday afternoon. Enjoy the rest of your weekend. Looking forward to catching up with you in a new session on Monday of your daily equation. Take care.